instructions. All right, so welcome everyone to another installment of TCS Plus, the original online seminar in TCS committed to the carbon-free dissemination of ideas across the globe since 2013. Before introducing today's speaker, let me start with a few quick announcements, beginning with a brief shout out to the other organizers: Clément Canon, Rachel Cummings, Anindya De, Sumega Garg, Gautam Kamath, Ilya Rosenstein, Oded Regev, Slil Shram, Noah Stevens-Davidovich, Thomas Vidic, and Eric Weingarten. So second announcement, in our next talk in 2 weeks, we'll have Jessica Sorrell, who's here in the audience from UCSD, who will tell us about reproducibility in learning. I'm looking forward to that. But before that, we are lucky to have another talk today by Shuichi Hirahara from the National Institute of Informatics in Japan. Shuichi has a number of awesome results on the general theme of meta-complexity and its use to prove complexity theoretic results. Today, he will tell us about his recent work following this theme on ruling out pH equivalents of Impagliazzo's 5 possible worlds, and in particular, an unconditional result in this space. I'm really looking forward to this talk. So Shuichi, without further ado, the floor is yours.
Thank you so much. It's a very nice introduction. So today I would like to talk about the joint work with Rahul Sansanam, which is about excluding pH Pessiland. So here is the outline of today's talk. I will first explain the idea of Impagliazzo 5 worlds, and then I would like to explain some recent progress on pH heuristica, and then I would like to explain metacomplexity, which plays a central role in studying Impagliazzo 5 world. And finally, I will explain our result. So in the most part of this talk, I will explain the background. I would like to explain the background of this work. So let me start by explaining Impagliazzo 5 world. In the very influential work by Russell Impagliazzo, he proposed 5 possible worlds that are consistent with our current knowledge on cryptography and complexity theory. So here we have 5 possible worlds: algorithmica, heuristica, Pessiland, minicrypto, and cryptomania. It is known that exactly one of them corresponds to our world, but currently we don't know which world corresponds to our world. For example, algorithmica is a world where P is equal to NP. In this world, any problem in NP can be solved efficiently, in particular in polynomial time in the worst case. But in this world, it is impossible to construct a secure crypto system. The rest of worlds corresponds to a world where P is different from NP, and it is further classified in this way. For example, the topmost world is called cryptomania. This is a world where there is a secure public key crypto system. Most researchers believe that our world is cryptomania because there are many candidate constructions of public key crypto systems, such as RSA crypto system. We haven't been able to break the security of such RSA crypto system, so that's why we believe that our world is cryptomania. But currently, we don't know whether it is really secure or not. There are other worlds, such as Pessiland. Pessiland is said to be the worst possible world, and the name comes from a pessimistic world. In this world, it is impossible to construct a private key crypto system, and at the same time, we can't solve NP efficiently on average. So this takes the worst of both results, in the sense that we can't construct a secure, we can't do crypto system as well, and we can't solve NP efficiently on average. Minicrypto is a world where it is possible to do minimal cryptography, in the sense that it's impossible to construct a public key crypto system, but it's possible to construct a private key crypto system. Finally, heuristica is a world where heuristics are efficient, in the sense that there are efficient heuristics that can solve NP on average, But at the same time, it means that we can't construct a secure crypto system. So we have 5 possible worlds, and it's known that exactly one world corresponds to our world. The ultimate goal of compressed theory and cryptography is to decide which world corresponds to our world. In particular, most of researchers believe that our world is cryptomania. So ideally, we'd like to resolve the conjecture that our world is cryptomania, and thereby we'd like to construct a truly secure public key crypto system. However, what's unfortunate is that researchers have made a little progress so far. So we'd like to propose a way to make a progress. Before explaining the proposal, let's explain the equivalent formulation of Pythagoras 5 world. So here we defined mini crypto as a world where there is a private key crypto system, but it is known that it's equivalent to the existence of pseudo-random data, and it is also equivalent to the existence of a one-way function, which is the result by hosted in Pythagoras Levin-Rubin. So we are going to use this formulation. Now, with this formulation in mind, let's propose to consider pH versions of 5 possible worlds. So previously, we considered polynomial time computable pseudo-random generator. Now, in order to make progress, let's consider pH versions of 5 possible worlds, or pH computable pseudo-random generator. Remember that pH stands for polynomial hierarchy, and it is defined to be NP to the NP to the, and so forth. It's the constant penny tower of NP. So what's the pH version of 5 possible world? Well, instead of polynomial time PRG, let's consider pH computable pseudo-random generator and the pH computable public key crystal system. And instead of NP being hard on average, let's consider pH being hard on average. Similarly, pH algorithmic is defined to be a world where P is equal to pH instead of P is equal to NP. Let me mention that this world doesn't have any implication to cryptography, unfortunately, because even if we have a pH computable public key crypto system, it is not useful for our daily life. But let me emphasize that this is completely theoretically interesting, especially because if you look at the definition of pH algorithmica, this is actually equivalent to the standard version of algorithmica, because it is known that P is equal to pH if and only P is equal to NP. So it's quite non-trivial whether these versions of 5 possible worlds can be excluded or not. Now, our main result is to show the equivalence between the existence of pH computable pseudo-random generator and the average case hardness of pH. So the equivalence between these. So in particular, this means that we can exclude pH Pessiland in the following sense. The definition of pH Pessiland is as follows. This is a world where pH is hard on average, and there is no pH computable pseudo-random generator. But we have shown that this is average case hardness pH is equivalent to the existence of pH computable pseudo-random generator. So this AND statement is unconditionally false, so we can exclude pH Pessiland. Note that this is conceptually quite non-trivial, because if you consider pH heuristica, it is still open. We don't know whether pH heuristica can be excluded or not. Although there are several progress on this. So in order to explain the details, let me quickly remind you of standard complexity classes. So this is a standard picture that you might be familiar with. In between P and NP, you have UP, which is a class of problem that can be solved by a non-deterministic polynomial time machine with at most one accepting path. And above NP, we have PH, which stands for polynomial hierarchy, and this is defined as follows. Sigma Kp plus 1 with K plus 1's level of sigma of pH is inductively defined as follows. It is Np raised to sigma Kp, and pH is defined as the union of all the constant levels of pH. And it is known that pH is contained in P space. Now, let's explain the basics of average complexity theory. It's important to understand this work. So let me explain the notion of averages. Let me explain the basics of averages complexity theory. So in the theory of averages complexity, we study a distributional problem, which is a pair of a decision problem, which is also called as a language, and a family of distributions. Here, for each input size n, we assume that there is a different distribution, d sub n. So this pair is called a distribution problem. And in the theory of averages complexity, we study whether this can be solved efficiently on average. More specifically, let's say you are given a random input x, which is drawn from the distribution d. Can we efficiently decide whether x is in the language or not with a high probability over a random input? So this is the notion of average extractability. But in order to formalize this notion, there are at least two ways to formalize this. One is called errorless heuristics, which is denoted by average p, and the other is called error-prone heuristics, which is denoted by Shuichi. The difference between these two notions are quite important. So let me explain what the definitions are. So Shuichi is the class of distributional problem that can be solved by error-prone heuristic schemes. More specifically, this is defined as follows. We say that a distribution problem L and D is in Shuichi if there is a polynomial time algorithm A such that if you pick a random instance X from the distribution D, the error probability of A is at most delta. So this is a standard notion of average extractability. Let me repeat this. You are given a parameter delta, and delta is given to the algorithm in a unary encoding. So in particular, the input length of A is at least the length of X and delta inverse, which means that when we say it is a polynomial time algorithm, we assume that the algorithm runs in polynomial in the length of X and delta inverse. Now, the probability over the choice of random instance of X drawn from D, that the algorithm outputs the incorrect answer is bounded by delta. This is the notion of error-prone heuristic scheme. Now, there is a stronger notion which is denoted by average p. This is a class of distribution problem that can be solved by so-called errorless heuristic scheme, which is actually equivalent to average's polynomial time. So in this notion, we additionally require that the algorithm is errorless in the sense that the algorithm is allowed to output either a correct answer or a special bottom symbol, which indicates that the algorithm doesn't know the answer. And we also require this condition, which means that the probability that the algorithm outputs the bottom symbol is at most delta. You can think of this notion as a SAT solver. So when you run a SAT solver, it is usually you get three possible answers. One is satisfiable, the other is unsatisfiable, or timeout. And the bottom symbol means timeout intuitive. which indicates that the algorithm doesn't stop in polynomial time. So these are two notions of average case tractability. And there's a, now let's define average case version of NP, which is denoted by distributional NP. Distributional NP is a class of distribution problem such that L is in NP and D is efficiently sample of polynomial time sample. So the idea of this definition is that we would like to analyze the average case complexity of NP with respect to efficiently sample distribution. In other words, we don't care about distributions that cannot be sampled because we don't know how to generate such an instance. And we would like to focus on analyzing average case complexity of NP with respect to efficiently sample distributions. Now, unfortunately, we don't know the relationship between average P and Hury P. Of course, average P is a subset of Hury P, but we don't know whether the converse is true. In particular, we don't know whether even if we have distributional NP is in Hury P, whether distributional NP is in average P or not. So when we consider average case complexity of NP, it is important to consider which notion we use. Now, let me explain some recent progress about pH heuristica. So in order to explain that, let me explain what's known about standard version of Impactors 5 world. In the standard version of Impactors 5 world, we have these implications. Namely, if we have a secure public key crypto system, we have a private key crypto system. And if we have a private key crypto system, then we know that NP is hard on average. Here, of course, it is hard with respect to Hury P as well, but let's consider average P here. And if NP is hard on average, then NP is hard in the worst case. Now, the compass direction of these implications corresponds to a central open questions in the theory of average case complexity. For example, the bottom blue implication corresponds to whether we can prove P is different from NP. If we can prove this, we can exclude algorithmic from a 5 possible world. Similarly, if we can prove the second implication, we can exclude heuristic. Proving one implication corresponds to excluding one possible world. And if we can prove all these 4 implications, we can conclude that our world is cryptomania. But unfortunately, these are quite central open questions in the theory of average case complexity and complexity theory. So there are many works that shows limits of our proof techniques. So for example, in order to prove that P is different from P, it is known that we need to develop new proof techniques that simultaneously overcome relativization, algebraization, natural proof barriers, and so forth. Similarly, in order to exclude heuristica, we need to use proof techniques that are not subject to relativization barrier, limits of black box reduction, nor impossibility of hardness amplification. Fortunately, there's a new paradigm, emerging paradigm about metacomplexity, which enables us to make progress on these difficult open questions. Informally, metacomplexity refers to the complexity of a problem themselves asking for complexity. Let me give one representative example of metacomputation problem, which is called MINCAT. This stands for minimum time-bounded Kolmogorov complex problem. And informally, this is the following problem. It asks to compute the minimum program to compute X efficiently. So MINCAT asks the complexity of generating X. So if you consider the complexity of MINCAT, it means it is the metacomplexity of time-bounded Kolmogorov complexity. Now, by considering such meta-computational problems, we can show that for that kind of a problem, we can show that worst case and average case complexity are equivalent. More specifically, we can show that the worst case complexity of mean KT and average case complexity of mean KT with respect to the uniform distributions are equivalent to each other. What's important about this is that this is proved by non-black box reduction. And previously, we didn't know whether there is a problem that where this was the first result that goes beyond the limits of black box reductions. Now, more recently, by using such a meta-computational approach, we were able to resolve a long-standing open question about worst case to average reductions. If we assume that UP is exponentially hard in the worst case, can we show that NP is hard on average? This was a long-standing open question because in order to prove this, we needed to use proof techniques that is not subject to limits of black box reduction and impossibility of hardness amplification. We don't know whether relativization barrier is applicable to here, but in order to prove this, we needed to overcome two barriers simultaneously. And by using a meta-computational approach, we were recently able to show that this implication, which shows that if UP requires the time complexity of 2 to the order n by log n, then NP is hard on average. In fact, the same paper contains a result about pH. So if we assume that pH is exponentially hard in the worst case, we can show that pH is hard on average. So this is a progress about excluding pH heuristica, because if we can reduce the time complexity 2 to the order n by log n to polynomial, we get this implication. So although there is a it's exponentially apart, this is the first non-trivial worst case to average case connection for pH. And the proof techniques is based on metacomplexity, although the statement has nothing to do with metacomplexity. So let me explain this metacomplexity in next. Do you have any questions so far? Okay. So now let me explain the basics of metacomplexity. So in order to explain the notion of metacomplexity, I need to first explain time-bounded Kolmogorov complexity. T time-bounded Kolmogorov complexity of X is often denoted by K superscript T of X, and this is defined to be the length of a shortest program that prints X in T steps. Let's take a look at the 3 examples. Let's consider the time-bounded Kolmogorov complexity of all 0 string. We can upper bound this Kolmogorov complexity by log n plus order 1, because in order to describe this string, we can consider this short program, print 0 n times. And the length of this program is at the most, in order to specify n, you have log n bits, and the rest part is just a constant, which doesn't depend on order, which doesn't depend on n, so you get order 1. Similarly, in general, we can upper bound Kolmogorov complexity of X by the length of X, because there is a trivial program saying that print X itself. And moreover, this is tight because by using a simple counting argument, we can show that the Kolmogorov complexity of X is at the most n-2 with high probability. So in general, the time-bound Kolmogene complexity measures how much you can compress a string by using a throat program. This is the notion of time-bounded Kolmogene complexity. Now, metacomplexity is the complexity of complexity, and there are many examples of metacomputation problems such as MCSP, MKTP, and MinKT. Here we consider MinKT, which is the problem of the computing the time-bounded Kolmogene complexity. Remember that T-time-bounded Kolmogene complexity of X is just the length of a shortest program that prints X in T steps. And MinKT is defined as the following decision problem. The input is X and T and S. Both of them are written in unary. And the problem is to decide whether T time-bounded Kolmogene complexity of X is at most S or not. This is the definition of MinKT. And there is an additive approximation version of MinKT as well, which is denoted by gap MinKT. Gap MinKT is the following problem. You are given X and T, and the problem is to approximate the T time-bound Kolmogene complexity of X, but you are allowed to have an order log n additive approximation. Here, P is some polynomial. There is a generalized version of MinKT, which is called MinKT to the A. This is the problem of computing the A oracle time-bounded Kolmogene complexity. And A oracle time-bounded T time-bounded Kolmogene complexity is just defined as follows. This is the length of a shortest program, but this program has oracle access to A. So instead of minimizing a program, we would like to minimize A oracle program. So that's the definition of A oracle time-bounded Kolmogene complexity. And MinKT to the A is defined as the problem of asking whether the time-bounded A oracle T time-bounded Kolmogene complexity of X is small or not. You might wonder that A should be reducible to MinKT to A because it seems difficult to minimize A oracle program, but in general, we don't know whether A is reducible to MinKT to A or not. We sometimes have MinKT to A is in NP to A because you can guess a small program and you can check whether it outputs X or not. So this is a problem in NP to A, but whether it is this upper bound is tight or not, it's a central open question in metacomplexity. In particular, it is not known whether MinKT is NP complete or not. Similarly, even if we assume that there is a pH oracle, we don't know whether it is NP hard or not. Now, let me explain why metacomplexity is useful to analyze average case complexity. In fact, it can be shown that average case complexity of pH can be exactly characterized by metacomplexity. Here, this notation means that for every oracle A in pH, gap MinKT to A can be computable in polynomial time. Remember that gap MinKT to A is an order log n additive approximation version of MinKT to A. What's important about this characterization is that we can get proof techniques of analyzing average case complexity by using metacomplexity. To be more specific, we can get average case hardness amplification result for pH by using this characterization. Specifically, if we assume that pH is easy on 1% fraction of inputs, then we can show that pH is easy on most instances. And the proof is given by going through the notion of metacomplexity in this way. So the exact statements are not so important, but at a high level, the reason why it makes easier to analyze average case complexity by metacomplexity is that if we consider metacomplexity, we can analyze average case complexity from the perspective of worst case complexity. And in general, worst case complexity is easier to analyze. So by using metacomplexity, it makes it easier to prove such a result about average case complexity. Now, the result I mentioned about the pH heuristic is proved in a similar way. So it's a statement about average case complexity, but it is proved by going through the notion of worst case metacomplexity. I will not explain the details of this result, but it is useful to keep in your mind this figure. So I will explain, we will use the same kind of figure in order to get the result about pH Pessiland as well. Now let me explain this work. So the main result of this work is to exclude pH Pessiland, and we were able to unconditionally rule out pH Pessiland in both uniform and non-uniform setting. Namely, even if adversary is a BPP algorithm or polynomial size circuit, we were able to show the following equivalences. We can show the following, basically 3 statements are equivalent. One is pH, the existence of a pH computable Pessiland generator, average case hardness of pH, and average case hardness of mediated pH. Our result is, let me emphasize that our result concerns error-prone average case hardness, whereas the previous result shows distribution. In the previous work, we considered errorless average case complexity. So in particular, the third statement means that mediated pH is distribution of pH complete, even in the setting of error-prone average case complexity. So in order to state our result more formally, let's recall the notion of pseudo-random generator, or PRG for short. Our function G, which takes a seed of length n and extends a pseudo-random sequence of length T of n, is said to be a pseudo-random generator secure against a class C if we have the following property. For every algorithm C in the class, the circuit C cannot distinguish uniform bits from the pseudo-random distributions. More specifically, we consider the following 2 probabilities. One probability is the probability that C outputs 1 on input uniform random bits, and the other probability is the probability that C outputs 1 when you are given a pseudo-random sequence G of R, where R is a random seed. And if these 2 probabilities are close to each other, we say that it is a pseudo-random generator. In general, we would like to maximize the output length of the pseudo-random generator. So ideally, we would like to have T to be polynomially large. So now let me state our result. In the case of non-uniform adversaries, we can show that the following are equivalent. The first statement is that pH is average is hard with respect to the uniform distribution. And here we consider a heuristic P/poly algorithm. Namely, this is a polynomial size circuit. The second statement is that mediated pH is average is hard with respect to the uniform distribution. So this statement means that mean candidate's pH is distributional pH complete. The third statement means that there is a pH computable Pessiland generator secure against P/poly, and this Pessiland generator extends the seed by 1 bit. The final statement states that there is a pH computable Pessiland generator which extends the seed polynomially, namely n to the c for every constant, which is secure against infinitely often polynomized circuit. So this result shows that if you consider error-prone averages hardness of pH, it is equivalent to the existence of pH computable Pessiland generator. In the previous work actually shows the equivalence between error-less averages hardness pH and pH computable heating set generator. So our result is analog for error-prone averages compressed heat. In the case of uniform adversaries, we get a similar result, but unfortunately, the result is a bit weak. So this is quite similar to the previous result, but in the uniform case, we consider BPP algorithm or randomized polynomial algorithms. We can show that these averages hardness of pH and averages hardness of mean candidate pH are equivalent to the existence of pH computable Pessiland generator that extends the seed by 1 bit. But ideally, we would like to also show that it is equivalent to Pessiland generator which extends the seed polynomially, but we were able to extend the seed just by c log n bits. So it's quite weak compared to the case of non-uniform case. But if we assume some technical condition which says that there is a Tully language error in pH which cannot be solved efficiently, we can also show that it's equivalent to the existence of a pH computable Pessiland generator which extends the seed polynomially. It is an interesting open question whether we can show the equivalence between the averages hardness pH and the polynomial stretch pH computable Pessiland generator. Now, let me explain how we can prove such a result. Actually, the proof techniques are more or less standard. The proof is can be proved by using this figure. So let's start by considering averages hardness of pH. Now, let's say we would like to construct a pH computable Pessiland generator. In order to do that, we can use a standard hardness versus randomness framework. In particular, there is a famous construction which is called Nissan-Wigderson pseudo-random generator. Nissan-Wigderson pseudo-random generator enables us to construct a pseudo-random generator based on averages hard problems. But if you just apply Nissan-Wigderson generator, the hardness is not sufficient. So we use hardness amplification theorem by using Yao's XOR lemma. By combining these standard proof techniques, we can construct a pH computable pseudo-random generators. Now, if we have a pseudo-random generator, we can show that there is an averages hardness for mean to the pH. And this can be proved by using the work of Frost, Lemberg, Levin, Ruby, and as well as recent work by Liu and Pass. By using their proof techniques, we can reduce the task of breaking a pseudo-random generator to mean pH. Intuitively, the reason is that by measuring the time-bounded Kolmogorov complexity of a string, you can check whether it is a pseudo-random sequence or it is a uniform random sequence. Now, finally, we can show that if mean case to pH is average case hard, then pH is trivially average case hard because mean case pH is a problem in NP to the pH which is equal to pH. So that's how we prove the equivalence. That's how we prove about the case of non-uniform case. But in the case of uniform, it's more technically more challenging. And in particular, in order to construct a pH compatible Shuichi generator, in general, we need to have average case hardness against non-uniform algorithms. In general, it is known that in order to construct some Shuichi generator with stretch order of n, we need to have average case hardness against algorithm that takes advice of order of n, which is denoted by w/log n here. And this is a class of average case algorithm which is given advice string of order of n bits. And this w/ notation means that the advice is powerful in the sense that it can depend on coin flips of BPP algorithms. If we have such an average case hardness against non-uniform algorithm, by using a hardness versus randomness framework, we can again get a pH compatible Shuichi generator. And in order to do that, we can't use disambiguous Shuichi generator, but there is a simpler construction called direct product Shuichi generator. And by combining again a hardness amplification theorem, we can construct a pH compatible Shuichi generator. But again, we need to consider a uniform algorithm. So we need to, it's not sufficient to consider non-uniform hardness amplification, and we need to use a uniform hardness amplification result. Now, what remains is that we need to start from average case hardness with respect to uniform algorithm. So we need to remove advice. So that's actually the most technical part. And we need to show that if we assume that there is a pH is average case hard with respect to the uniform algorithm, we need to show that it is average hard with respect to order log n bits of advice. And intuitively, this can be done by brute forcing advice. So we enumerate all possible advice, which are polynomially many, and then we can choose which advice is good. That's why we just get order log n. And then we can also show that in this argument, it is important to consider polynomial times some probability, but there is a theorem by Impagato-Levin, which shows that in order to sample the average case hardness of NP with respect to the uniform distribution is hardest in the sense that if it is average case hard with respect to the uniform distribution, it is also hard with respect to some polynomial times sample distribution. By using that, we can make uniform distribution to polynomial times sample distribution. So that's how we prove this result. Finally, let me explain the landscape around pH patient. So in the previous work, we showed that in the case of errorless heuristics, average case hardness of pH is equivalent to the existence of a heating generator and the worst case complexity of mincated pH, as well as average case hardness of mincated pH. What we showed in this work is that in the case of error-prone average case complexity, the average hardness of pH is equivalent to the existence of pH compatible pseudorandom generator. Unfortunately, there is a gap between error-prone and errorless heuristics. If we can close this gap, we can get a larger equivalence between pH compatible pseudorandom generator and worst case compressive mediated pH. In a different joint work with Raffel Sansan, we have shown a sufficient condition to close gap. We showed that if this gap can be closed, if pH has an interactive proof system with pH computable honest prover. We haven't been able to construct such a interactive proof system, so it's not, we haven't been able to close the gap between these error-prone and errorless heuristics, but it is an interesting open question. Now, let me finally conclude this talk by giving approach toward excluding the standard version of heuristica and Pessiland. In the work of Impalgazzo Levin, they implicitly showed that if Pessiland can be excluded, if some kind of time-bounded Kolmogorov compressed is NP heard, T-time-bounded randomized Kolmogorov compressed is NP heard, and the T-time-bounded T-time reductions. In our work, we showed that heuristica can be excluded if gap mediated is NP heard. So these results suggest that if we can prove NP hardness of time-bounded Kolmogorov compressed, we can exclude both heuristica and Pessiland. So our result shows distributional pH hardness of mediated pH. And if we can show that gap mediated or mediated is NP hard, we can exclude the standard version of heuristica and Pessiland. So in general, understanding metacompressed, the compressed of metacompressed would enable us to exclude heuristica and Pessiland. So to conclude, our result gives further evidence that metacompressed would play a central role in excluding heuristica and Pessiland. And we believe that the metacompressed of time-bounded Kolmogorov compressed will play a central role in excluding Pessiland. So there are many interesting open questions. For example, can we show the equivalence between a polystorage pH compatible pseudorandom generator against uniform adversary and average hardness of pH? And one interesting open question is whether we can combine these two work to get to construct a pH compatible pseudorandom generator from the worst case exponential hardness of pH. So far, we haven't been able to combine these work because there is a gap between error-prone average hardness and errorless average hardness. Another conceptually interesting open question is to exclude pH minicrypt. In order to do that, we need to formulate pH minicrypt in a theoretical interesting way, and we need to exclude pH minicrypt. I believe that these are interesting open questions. Thank you so much for your attention. That's it.
Thanks, Shuichi. A lot of clapping emojis. Open the floor for questions. Okay, let me get the ball rolling. So Shuichi, among the five worlds, let's say the pH counterparts of the 5 worlds, if you have to guess, which of the 5 worlds would you put your money on?
Well, certainly this is the most difficult to exclude.
Mm-hmm. And
I do think that it is also very difficult to exclude pH heuristica. This is where although there is a progress about the worst case to average case connection to for pH. In order to make further progress, we needed to overcome a relativization barrier. So we haven't been able to get the proof techniques that overcome relativization barrier. So in order to make further progress, we would need new proof techniques that isn't subject to relativization barrier.
And I guess during the talk, maybe it wasn't quite clear to me. So Algorithmica and pH Algorithmica are the same. Are there other clear connections between the standard 5 worlds and these pH counterparts?
That's a good question. No. So even for pH heuristica, it's not known whether it is equivalent to heuristica. Actually, it is a long-standing open question whether pH heuristica is equivalent to the standard version of heuristica. So the question is actually equivalent to showing that if distributional NP is easy, then can we show that distributional pH is easy? It's another open question in the theory of averages comparison. And even in the case of pH Pessiland, it's not comparable to the standard version of Pessiland. Yeah. So in general, these are different versions.
Okay, thanks. Okay, so any other questions from the audience? Going once, going twice, going thrice. Okay, well, in that case, let's thank Shuichi again for a great talk.
Thank you.
And yes, I guess we'll see you again in a couple of weeks for Jess's talk on reproducibility in learning. Thanks again, everyone. See you again soon.